Hello, I want to welcome you to today's lecture. Today we'll be talking about stoichiometry. Stoichiometry is a very interesting topic, and I do hope at the end of this class you would enjoy every bit of it. Let's take it off from there. As usual, I'm going to start with a wonderful quote. The quote is from Aristotle. Aristotle is a great scientist when he lived. He said, we are what we repeatedly do. Excellence then is not an act, but a habit. I'll leave you to think over these quotes. All right, let's take it off. Now, the main learning objective we're going to be addressing today is that at the end of this class, we'll learn how to use the mole concept and the factor unit method to do mole-to-mole and mass-to-mass calculations, stoichiometric calculations. That is our main learning objectives. We're going to do mole-to-mole, we're going to do mass-to-mass stoichiometric calculations. And the basic thing we're applying there is our previous knowledge of the mole concept, and then the factor unit method, both of which we did, chapter 1 and chapter 2, respectively. Now, let's take it off from there. Now, what is stoichiometry? Stoichiometry is a term used to describe the quantitative relationship between reactants and product in a chemical reaction. In fact, when the chemical reaction is written, I mean a balanced chemical reaction. Any reaction that is not balanced is not a valid chemical reaction. A valid chemical reaction written with the balanced coefficient is a reaction whose reactant and product can be related quantitatively. And the term that used in describing that relationship is what we call stoichiometry. Now, of course, it is purely based on the balanced chemical equations. If we use that, then we can interpret the reactions in terms of the mole concept we did earlier, and then we can use that to solve problems using the factor unit method. Of course, the factor unit method uses the dimensional analysis problem to keep your desired quantity on top and keep the one you don't need below and then cancel it. So that is exactly what we're going to be applying today. I remember one of my students in one of the class asked me, does stoichiometry actually involve just conversion or just like? No, I said no, it is not just like, it is conversion. What we're going to be doing today is just conversion using mole ratio of a chemical equation, and where it is necessary, we bring in the molar mass, particularly by the time we talk about mass-to-mass conversion. Let's take it off from there. First of all, we're going to be looking at the mole-to-mole conversion. The mole-to-mole conversion scenario is the shorter scenario whereby you are given a mole of one substance and you want to convert it to the mole of another substance. It is very short. You don't need, in mole-to-mole conversion, you do not need there. What we don't need here is that we don't need the molar mass. What we simply need is the mole ratio of a reaction. So if we have reaction A going to reaction B, the mole here is A is to B. That is what I need in mole ratio. You're going to give me a mole. I'm going to take that using the mole ratio of A is to B to convert it. So the good scenario is that, assuming I'm given mole of A, if you look at this, I've been given mole of A from here. I have moles of A given to me. This is mole of A. Then this mole of A, I'm going to take it and convert it to moles of B. That is exactly what we're going to do here. So, and what am I going to use to convert it? Now, since my A and B is balanced by the coefficient of AB, the small letter A and small letter B, I'm going to put, since I'm looking for my B, the small letter B moles is going to be on top, and my small letter A is going to be below. And when I multiply my moles of A times any of this, you find out that moles of A is going to cancel moles of A, and I'm going to be left with only moles of B on top. So we get this from a balanced chemical reaction. Like I told you earlier, for stoichiometry to be valid, to work, you need a properly balanced chemical equations for this to actually work. And now let's just put this immediately into practice. Okay, before I go over there, okay, yeah, let's just kick it off immediately. No need to talk too much. The best thing is to kick it off immediately. It says, How many moles of water are formed when 25 moles of oxygen react with hydrogen according to the following equation? Now, I try to highlight or put the coefficient in red just to tell you the emphasis that is placed or the premium placed on a balanced chemical reaction. Now, the first thing you need to do, what do we want? Remember, at any stoichiometric problem involves solving for one unknown at a time from another known. So you solve an unknown from a known. You cannot be solving 3 variables at the same time. So what we're going to do, what do we even say? The question says, is looking for how many moles of water? That's what we're looking for. And we're going from what? 25 moles of oxygen. So simply, let me interpret this question. What I'm looking for here is that I'm going from moles of oxygen to moles of water. That is basically what this question is. So what it means is that I need to set up some conversion factors. That's what I'm going to do. I'm going to set up conversion factors to know where this goes to. Of course, the relationship is already balanced. The ratio is 2 of hydrogen is to 2 of water. That's what we have there. Now, what this thing simply means is that if this is my conversion ratio, it means that at any point in time, if I'm finding the relationship between that's not oxygen. So 1 mole of oxygen is to 2 moles of water. It's going to be, in one scenario, I can have 1 mole of oxygen on top divided by 2 moles of H2O. Or I can have a scenario whereby I have 2 moles of H2O on top, and I'm going to have 1 mole of oxygen below. Now, these are 2 scenarios. These are 2 conversion factors I can use to solve this problem according to the mole ratio from the balanced equation, which is 1 mole of oxygen to 2 moles of water. Now, what we decide what I'm looking for is which of these, the one I'm going to be using, depends on what I'm giving. So I'm giving that of oxygen. What it means, I want when oxygen is low. And the one that oxygen is below in a fraction is this one. So this is the conversion factor I'm going to use. Now, if I move that to the right, to the left side, what am I going to do? Now, you see, I'm going to start. You always go from the known. The known is 25 moles of oxygen. I'm going to draw my square bracket. Now, I'm using this conversion factor because the oxygen is below. And if you look at it, diagonally, oxygen has to be low. So it's going to be 1 mole of oxygen on top 2 moles of H2O. And then if I try to cancel with a different color, let's see. A mole of oxygen cancels a mole of oxygen. And what do you have here? 25 times 2 is going to give us what? 50. Of course, there are 2 digits here. I can just put 50 moles of H2O. And this will be my answer. So simply what you do here is just a typical case of a conversion problem. Just that is exactly what we have done. Let's go to the next problem. The next problem says, how many moles of hydrogen are required to react with 25 moles of water? Again, let's see what we need to do here. Again, the relationship is between hydrogen and oxygen. So the relationship is 2:1. So basically what we still started with the oxygen. So my major preoccupation is to convert from moles of oxygen to moles of water. That is what I'm looking for. And then remember earlier I wrote the conversion factors. Let me write it again. The conversion factor I can use is 1 mole of oxygen over, this is 2 moles of hydrogen. 2 moles of hydrogen. Or I can also use 2 moles of hydrogen over 1 mole of oxygen. This because the relationship is 2:1. However, I'm looking for hydrogen. What it means is that my hydrogen is going to be on top. Again, I start. So I'm going to have 25 moles of oxygen. I'm going to draw a line as usual. I'm going to try to draw this line. We'll give you, now, which one am I going to use? Again, let me circle the one I'm using. It's hydrogen, the one hydrogen is on top and oxygen is below. That's what I'm going to use. So I'm going to be using this one. This is what I'm going to be using. So if I bring that one in again, it's going to be, I need to change my color, sorry, red. So it's going to be 1 mole of oxygen below, and again 2 moles of hydrogen above. And I cancel out. If you cancel moles of oxygen, cancel moles of oxygen. If you multiply again, this is going to give you 50 moles of H2 will be produced with that. So that is how we do those problems. We do another one. I still have some more examples. Remember, always remember in my class, I do a lot of problems, because in solving more problems, that is the only way you're going to be competent or more comfortable with this concept. This one again is phosphorus react with hydrogen to form a phosphine gas. We call it phosphorus trihydride. What's the question? It says, how many moles of this guy are generated from 12.5 moles of this gas? So we're going from, look at the question now. The question says you're going from moles of, let's look at the relationship first. So this is 1 mole, 1 is to what? Well, look, 1 is to 4. So we're going from moles of P4, that's what we're going to, basically, to moles of PH3. That's what we're doing here. And again, we're going to find a common relationship. We're going to find the conversion. The conversion is 1 is to 4. So what that simply means is that I can have two conversions here. I can have 1 mole of P4 over 4 moles of PH3, or I can have 1 mole, no, I can have 4 moles rather. I can have 4 moles of PH3 divided by 1 mole of P4. These are the two conversion factors. But what will decide what I'm going to use is what I'm looking for PH3. So therefore, the one with PH3 is going to be on top. So technically, I'm going to be using this one. So what I will do now is to start. So I have 12.5 moles. So I'm going to say 12.5 moles of P4. Again, I draw my line. 12.5 moles of P4. Using that one, of course, you see 4 moles of PH3. I'm looking for PH3. It's going to be on top, and this is going to be below 1 mole of P4. And then if I cancel again, this cancels this. And if you multiply 12.5 times 4, we're going to be getting, again, you're going to be getting 50 moles of, you're going to be getting, sorry. This is in 3 digits, so I'm going to put this in 3 digits. So this is 50.0 moles of PH3. So this is what we're going to get. All right, so you can always pause this video, try out a few problems on your own, and always come back to check for your comprehension, okay? All right, let's go to the next one. Again, relating the phosphorus trihydride, it says, how many moles of hydrogen are needed to react with 12.5 moles of P4? Let's look at the relationship. The relationship here is 1 is to 6 hydrogen. That's what we have here. Again, if we're going to write the conversion factor, at a point I'm going to stop writing the conversion factor, but it's good you get comfortable and know the origin of how that came about. So I'm going to have 1 mole of P4 over 6 moles of hydrogen. This is what you're going to have at the point. Or you're going to have 6 moles of hydrogen divided by 1 mole of P4. So now, which one am I going to use depends on what I'm looking for. What am I looking for? Say, how many moles of hydrogen? I'm going to use the one that hydrogen is on top, which is this one. That's what I'm going to use. So that is what I'm going to use. I'm going to use the one that hydrogen is on top. Now, and I'll start with what I was given. So I was given 12.5 moles of P4. Again, I'm going to draw my table. Now I want this one to be down, so it's going to be 1 mole of P4. I'm using this one, remember that. And then it's going to be 6 moles of hydrogen. Now if I cancel with my green, we cancel this, And my answer is going to be, if you multiply 12.5 times 6, it's going to give us 75.0 moles of H2. All right. So this is all we're going to do in mole to mole conversion. Like I said, you can always pause this video and try these problems yourself before coming back to see if you got the answer correctly. Now, the next thing we're going to be talking about here is mass to mass conversion. Now, I like to test it. The mass to mass conversion is just a modification of the mole to mole. Now, we've just expanded the most. This is an expansion of mole to mole. That's exactly mole to mole. What has happened here? So if you look at the previous one we had, the mole to mole, we started from here and then we went here. But we've added pieces to the right and to the left because we're talking about mass. So basically, if you're going to convert from mass of A to mass of B, particularly grams of A to grams of B, of course, if you're giving something in kilogram, you have to take it to grams because the molar masses are measured in grams. We've added something to this side and to this side. That's exactly. So if you look at it, if you kind of look at it, you find out that it is just addition to what we had before, to the mole to mole conversion. You are still going to do the mole to mole thing, but first, you have to convert the mass of A using the molar mass and convert it to its mole. And then when you get the mole of B, you have to now take it to its mass using the molar mass. Now, so the two new things that come into play at this point is that the molar masses come into play. Those are what you use for conversion in these steps. In this step and in this step, you're going to use the molar mass for conversion. So let's take this out by solving problems to make us understand what a problem is. It says, how many grams of water are formed from 14.7 grams of oxygen according to the following equation? That is the problem, according to the following equation. Now, let's do this. So, the first step we need to do is to, first of all, I tell students, you're going to figure out the mole ratio. Of course, we're looking between oxygen and water. Of course, the mole ratio we have here is 1:2. That's good to situate that. The second thing you need to do is to, since you're looking for grams, the two things you're working with, you need to get their molar masses. So we're going to get the molar mass of oxygen and molar mass of water. Let's do it. So we know that oxygen is O2. O2, if you look at the periodic table, oxygen is 16.00. Okay, I like, right, is O2. So O2 is going to be 2 times 16.00. And when you multiply this, it's going to give you 32.00 grams per mole. That's what we get. And then let's calculate that out. Water. H2O. H2O means 2 hydrogen, 1.01, plus we have oxygen, 16.00. If you add everything together, this is going to give you 18.02 grams per mole. Now, so the basic idea here is that we want to look for, what we want to do here is that we want to convert from grams of oxygen to grams of H2O. However, we first of all have to convert, look at this chart. You have to first of all convert the grams of oxygen to moles of oxygen using each molar mass. So that's the first step we need to do. So we're going to draw a long table to do this. So what I'm going to do, I'm going to start with my, so if I put my oxygen here, how much oxygen do I have? 14 grams. So it's going to be 14.7 grams of oxygen. I'm going to draw a long line. I'm going to draw the line as I move. Now, 14 grams of oxygen is what so I have to convert it to moles of oxygen using the molar mass of oxygen. Look at the molar mass of oxygen here. So it's going to be 1 mole of course, if you're going to do that, you have to cancel the grams. So 1 mole of oxygen is going to give us 32.00 grams of oxygen. Now, again, I draw another line. If you want to always cancel at any point, that makes better so that you know that you're not going to be wrong by just canceling immediately. And then the next one, we have it now. Remember, let's go back to this. We've converted from mass of oxygen to mole of oxygen using each molar mass. Now we're going to convert from mole of oxygen to mole of hydrogen using the stoichiometry coefficient of the balanced equation. So that's what we do next. So that's what we're going to do. So we're going to convert from moles of oxygen to moles of what? Water. The ratio is 1:2. And since we're looking for water, water is going to be on top. So it's going to be, I'm going to use some called 2 moles of water divided by 1 mole of oxygen. 1 mole of O2. And if you cancel this, let me try to draw a distance. If I want to cancel that, now cancel it with my green, it's going to be this guy cancel, this guy will cancel. And I'm left with mole of oxygen. Now, if you're left with mole of oxygen, we're going to finish it now. We're not looking for moles. If you're asked to stop in moles, you can leave this. But this question is taking you what? To mass. It wants you to finish it up in mass. So, and what are we going to use? If we have moles of water, we're going to use the molar mass to convert it to the mass of water, or H2O. And we know 1 mole of water contains 18.02 grams. So what that means, we know that 1 mole of H2O. 1 mole of H2O contains 18.02 grams of H2O. So, and again, I want to cancel with my green. So moles of water cancel with moles of water. And if we multiply everything together, we're going to get 16.6 grams of H2O. That is exactly what you get. So you see, the basic thing that has just happened here is that this is a little bit longer than mole to mole, because you have to first of all convert it from mass to mole, and then again you need to take it away from mole using the molar mass of the second stuff you're looking for. Let's do another problem. Of course, let's do another problem. That's the way we get it. So now, again, we're still using this. It says how many grams of oxygen are required now. We're looking for oxygen to react with 14.7 grams of oxygen. So again, we want to convert from grams of O2 to, that's what we're doing, from grams of O2 to grams of hydrogen. Remember, you can look for 2 things, only 2 things at a time. The only thing we missed before was that we didn't calculate the molar mass of hydrogen, which we can do now. The molar mass of hydrogen is H2, of course. The molar mass of this guy will be 1.2 bracket 1.01. That will give us 2.02 grams per mole. That is the molar mass of oxygen. So let's start. Again, if we start from 14.7, that's what we're going to do, like we did before. So it's going to be 14.7 grams of oxygen. I'm going to draw my line again. Okay, so 14 grams. So I'm going to first of all, again, convert it to moles of oxygen, as usual. So it's going to be 1 mole of oxygen. It's going to divide, what's the molar mass of oxygen? 32 grams of oxygen. Again, I pull my line and I cancel out with my green. Gram of oxygen cancels grams of oxygen. The next thing I do is I take it to moles. Mole of oxygen to mole of hydrogen. What's the mole ratio? The mole ratio is 2:1. So it's going to be 2 moles of hydrogen over 1 mole of oxygen. Again, I cover this my line, and I can cancel out this. We cancel this. And the good thing to always cancel out at any point in time is that it gives you an idea whether you are correct or not, or whether you're making a mistake or not. If you don't always do that, you might be making a lot of mistakes. Then the next thing, it says we're going to convert from moles of oxygen to mass of oxygen using the molar mass. So what does that mean? We know that 1 mole of hydrogen will contain 2.02 grams of hydrogen. And again, we're going to cancel. If we cancel, mole of oxygen, of hydrogen cancels moles of hydrogen. And when you multiply everything here across, that will give us 1.86 grams of oxygen. 1.86 grams of hydrogen, sorry. This is exactly what you're going to get. Now, so we'll go to the next problem. The next problem says, determine the mass of phosphorus trihydride generated when 10.35 grams of P4 react with excess hydrogen according to the following equation. Now, we want to go from grams of P4 to grams of pH3. That's what we're looking for. So what we basically need to do first is to calculate the molar masses of the relevant things we need. So we need P4, so let's calculate the molar mass of P4. So P4, of course, will be 4 times. If you look up the molar mass of phosphorus, it's going to give you 30.97. This will, if you multiply this, it's going to give us this grams per mole. And again, the molar mass of pH3, so will give us 1 mole of phosphorus, 30.97, plus, there are 3 atoms of hydrogen there, so it's going to be 3 bracket 1.01, and that will give us 34.00 grams per mole. So we have what we need to solve this problem. So let's just start it. Remember, again, what we're doing here is that we're converting from mass of P4 to mass of pH3. And if we take it off from there, it's going to be 10.35 grams of P4 then convert it to mole of P4. Remember, you have to first of all convert it to mole. So 1 mole of P4 we weigh 123.88 grams of P4. This is what we get first. And then we continue. The next one. So you can easily cancel. Let me cancel. So this grams of this cancel grams of this. The next thing will be, now what's the mole ratio between P4 and pH3? It is 1:4. You look at it, 1:4 ratio. So what it means is that we're going to have 4 moles of pH3 for every 1 mole of P4. Again, we can easily cancel this. You see this, we cancel this. And lastly, we want to convert from moles of pH3 that we have to the mass of pH using the molar mass. What is the molar mass? 34.00. So we're going to say 1 mole of pH3, of course, is going to give us 34.00 grams of pH3. And when you multiply everything together, it is going to give you 11.36 grams of pH3. And that becomes our answer. And again, you can always cancel this. You can always cancel this. We cancel this. I like using a different color to always cancel. So this is how we solve this problem. We go to the next one. Of course, stoichiometry is just problem marathon, and that is the only way to get competent in doing it, by solving numerous problems. It says calculate the mass of P4 needed to produce 22 grams of pH3. So now, you see the kind of change in the other one. So what we're looking for here basically is that we want to find mass of pH3, because we're given that here, we want to convert it to mass of P4. So that's basically what we're doing. Of course, we have the molar masses already calculated for both those two guys. We have it here already. If you go here, we have P4 to be 123.88. We have pH3 to be 34.00. So we already did something between these two earlier. So this one now, the first one went from here to here. Now we're going from here to here. So just as a reminder, you can always write it. So pH3 is 34.00 grams per mole. So I'm going to try to take away this. Let me make it properly. Okay, so pH3 is 34.00 grams per mole. And then P4 is 123.88 grams per mole. That's what we have. Then the next thing we're going to do is to start the problem. So we have 22.0 grams. I hope I'm not covering that. Okay, I'm not. I just want to make sure I'm not. So we're going to move. So we start this one. We're going to convert. So we move 22.0 grams of pH3 and then we're going to convert it to mole. So to convert that to mole, of course, we know 1 mole of pH3 will give us 34.00 grams of pH3. And then we move from there. You can always cancel so far this. We cancel this. And then go back to the drawing board. So what next? We want to convert from moles of pH3 to moles of P4. So look at what it's going to be. What's the mole ratio here? Now, since we're looking for P4, P4 is going to be up. So it's going to be 1 mole of P4 is to 4 moles of pH3. And then we're not going to convert from moles of pH3 to mass using the molar mass. So what is going to be? What's the molar mass of P4? It's going to be 1 mole. Oh, sorry. Didn't change that to. It's going to be 1 mole of P4 will give us 123.88 grams of P4. So what does that tell you? We now go and try to cancel. So if I cancel moles of pH3, cancel mole of pH3. Mole of PF4 will cancel mole of PO4. So it shows that we are correct. It's everything cancelled that we don't need. And we're only left with the one we need. So that will be equal to what? If you do the calculation, punch it in your calculator, you're going to actually get 20.0 grams of P4. And that is going to be our answer. All right. So we go to the next problem. You see, almost getting to the end. The next problem here, I just decided to use this problem to stimulate you a little bit to think beyond just the mass-to-mass conversion. You see, in stoichiometry, you can do any type of conversion. It doesn't have to be just mass-to-mass. You can do particle-to-particle conversion. What it means is, you look at this question, it says, how many particles of hydrogen are needed to produce 22 grams of pH3 according to the equation, just like the equation I've used earlier. So we're looking at the relationship between this guy, which is 4, is to hydrogen, which is 6. However, now we're looking at it for the molecule, but we're starting this. So basically what we're going to do is that you're going to convert from moles of this guy to from mass of pH3 to mole of pH3. And from mole of pH3, you convert it to molecules of to moles of hydrogen, and from moles of hydrogen to molecules of hydrogen. So basically, you can modify this to go into the particle. And particles can be, of course, molecules. It can be ions. It can be atoms. It can be formula unit. It doesn't matter. The same thing here. You can also modify this. So the mole is a connection to the particles. It can go any direction. It can become molecules, like I said. It can become ions, atoms, or formula unit. So the mole is a connection. So what the problem wants us to address, I'm going to do it this way, is we want to convert from mass of pH3 to molecules of H2. Remember this conversion. The 1 mole of any stuff, including hydrogen, will contain 6.022 times 10 to the power 23 molecules of hydrogen. So just to let you remind you. So how do we do this problem? It is just basically the same thing. The difference is that when we go to the moles, instead of going to the mass, we change road, we change the pattern and begin to go to the particle. Instead of going this way, we go down this way. So we're going to be taking, let me use a different color. We're going to be taking this route. Instead of going this route, we're changing route. And that is exactly what particle stoichiometry is all about. So let's see how the problem is solved. So let's start. Of course, we have 22.0 grams of pH3. I'm going to draw a line. This is going to be a longer line. I'm going to make it a little bit longer. It doesn't matter. It's not an art. It doesn't have to be beautiful. Then I'm going to convert it to moles of that guy. So what am I going to do? So it's going to be 1 mole of pH3 gives me, of course, 34.00 grams of pH3. Again, I convert this to what? Now, you can easily start striking out stuff. It doesn't matter. So I'm going to strike out this and strike out this. Now, what's the mole ratio between hydrogen and phosphorus trihydride? It is 6 moles to 4 moles. So that's the next thing we do. So we're going to do that. It's going to be 6 moles of hydrogen will give me 4 moles of pH3. Again, I want to cancel. If you cancel out this, we go with this. Now, one more step. Remember, if I'm looking for the mass of hydrogen, I'm going to switch to the molar mass of hydrogen, but I don't need it at this point. What do I need? What I need is the molecules of hydrogen. And what's the relationship I'm going to use? 1 mole of hydrogen contains this number of molecules. And since I need it in molecules, what it means is that my molecules is going to be on top. So what it means is that a mole of hydrogen, of course, according to this conversion, a mole of hydrogen will contain 6.022 times 10 to the power 23 molecules of H2. You can make this thing a little bit longer. And then let's try to cancel. If we cancel again, you see most of hydrogen cancels most of hydrogen, and you're left with molecules of hydrogen. So this is how you do this kind of problem. Now, I just want to throw in this problem to make you think more broadly and understand this concept. However, this will not come up in your exams. For now, if I'm going to give you this kind of problems, it's just going to be a practice and things we do in the worksheet. Or if I have to, I can give you maybe a take-home assignment for that. So if you punch this in your calculator, what are we going to get? Let's put that in our calculator. If you punch it in, you're going to get 5.84 times 10 raised to power 23 molecules of H2. So these are how much we're going to be doing for stoichiometry today. I want to thank you for listening. Make sure you spend time to listen to these videos time and again and practice on how to solve those problems and examples I have in them. Thank you for listening and have a wonderful day. Bye at this point.